Okay. Let me just verify that. Yeah, looks good. All right, put any questions in the chat. One thing I want to just make, okay, so basically, what's the plan for the rest of the, course? So today we're going to go over views, indexes, and also transactions. On Monday, we're going to go over basically security and authorization. Plus, I'm going to talk a little bit about cloud computing and databases. The course book doesn't really deal with that because it wasn't really around back then, at least not as pronounced as it is now. So really, I mean, the cloud is where it's at when it comes to databases. So I'm going to give more kind of an AWS, Amazon Web Services oriented view into cloud computing. But it'll also pertain to the other major cloud platforms, IBM and Microsoft. So so that should be kind of interesting because that'll show how you actually, I mean, any realistic work these days you'll deploy to the cloud. I mean, well, there are certain cases where you would have to be on premises, but generally speaking, you go to the cloud. Okay, so if there's any questions, just put them in the chat, and we'll just go into views and indexes. Actually, I'm sorry, there was one more thing I wanted to say, and that has to do with the makeup recitation. So the makeup recitation, again, I just want to repeat so everybody understands how it works. First of all, it'll only be me holding the makeup session. So the TAs won't be holding makeup recitations. So it'll all be in this Zoom channel that you're on right now. That's where the makeup recitation will be. And we'll just prepare a form where what you do is you just declare which recitation can you do 100% of. And then I'll just call on people to kind of show their work. You know, probably the harder problems on recitations that they claim for. You will get the full points though, because you're making a claim that you could do any problem on that recitation. So then you can pick recitation, basically 1, 2, 3, or 4. So just one of them, you can pick one of them and get the full points based on that. So I hope that's clear. Another thing also is that because we'll have a little bit better idea of exactly what is covered, what's going to be covered, I'm going to release the old exams. I'm going to have to dig around and find them. I'm going to release the old exams on Monday, and then so the makeup recitation will be exactly 1 week from now, and then the following Monday we'll have a big review session. And that big review session, I'm actually thinking about, actually coming in, and we'll hold that in person. But I need to check that out a little bit. I've already had COVID, so I mean, I'm fine, but I'm not really sure exactly. I'll have to kind of look around a little bit to see if we're quite ready, but I think we might be getting ready to do that. But maybe the review session is when we'll actually get to meet in person, which is kind of amazing that it's been like 2 years without that, which is crazy. But anyways, okay, so when will they open up registration? That's a good question. I've been trying to kind of, first of all, another thing about the exam is it's just going to be a written exam. There was some business about like having it being a digital exam, but then I looked into it and I think it's just going to be a nightmare because I know that basically they have the software they have that it's just going to be, let's see. Yeah, you can do a makeup recitation for just one of them. Somebody asked a direct question here. So you basically just are going to make up, if for instance, you missed one of the recitations completely, then you just declare that one. But you have to be able to do every problem on the recitation you claim. Open up the register. I'll try to bug them about it. My assumption was that it was going to happen very soon. But I'll just make a note of that. If you guys send messages to Student Expedition, the thing is I can't really open up that. I can register for the exam on LADA, but not on Student Debit. Yeah. Anyways, the exam is going to be a written exam. It's going to be on paper. I'm going to print it out. I'm going to bring it over there, and I'm going to like plop it down with them, and I'm going to print a ton of extra exams. I know it's a waste of paper, but I'm going to do it because I never, ever, ever find it acceptable. Even if a student doesn't register for the exam, but then just shows up, they always ask me, well, should they be allowed to take the exam? And I always say, yes, yes, of course they should be allowed to take the exam. I think that they want, I don't know. I'm kind of, in general, I'm against this. It feels like there's just a little bit too much bureaucracy around this. I mean, too much like control. It's not my philosophy. I generally think that it's not hard to count up the number of students in the class, get a kind of an approximation of how many would show up, and then just let them show up without having to go through some rigmarole, some registration process, and blah blah blah. I'm against it, but they should have it open. But like, please bother student X, because I can't do anything about it. I've sent them. I mean, I'm going to send them another message, but all right. So somebody already, yeah, the digital exam is off. I'm not going to do it because the digital exam, they want it to, like, you guys bring your own laptops, and then you have to install some software on your laptop that would block access to the net. And the thing is that some of you guys have Linux laptops, and my experience is it's just going to be a complete pandemonium getting that stupid software to work when it's just like the, no, it's going to be just like I want to do it the old-fashioned way. It's going to be I mean, I thought originally they would have their own computers there, and you guys would sit at a terminal. But no, it's like you guys have to show that some software is installed on your computer. It just seems really like it's not going to work. I'm just, generally speaking, I don't know if you guys, I mean, I'm not sure if they talk about this, but I am a giant believer in what's called Murphy's Law. I don't know if you guys have heard. I'm sure you guys have heard. Maybe the På Svenska there. I don't know what it's called in Swedish. But the idea is that if anything can go wrong, it will go wrong. That's just, we use it in another course, and I think it works. Yeah, I'm going to wait and see if it works. I don't want to be the guinea pig for this thing. The thing is that Lagen om alltid. Yeah, okay. Yeah, exactly. It's the truth. I've seen it 1,001 times. It's like, and then I mean, I used to get so offended when I heard people saying this, like, KISS principle, keep it simple, stupid. But I've learned that it's not, don't take it as an insult when someone says KISS. They're not calling you stupid, but they're calling people in general are stupid. It's just people are in general disorganized. And then it just becomes like, no, I mean, yeah, anyways. Maybe it's why I'm not really a big manager. Because I always tell, when I manage people, I always say the default is no. Because it's just like, let's keep it simple. Let's just let things roll and keep it simple. That's kind of my management philosophy. But anyways, when someone says here that they use it in a different course and it worked fine, did it work fine with Linux? Did people have, because people are, I mean, people are going to have Linux on their laptops. What about them? Yeah, exactly. And then it's going to be just like, oh, the people who show up with a Linux laptop, it doesn't work. And then what about people who have like an older version of Windows or an older version of like the Mac OS? And then what about it not working for them? And then them just burning up. No, we couldn't use Linux. Yeah. Then you can lend a laptop. Yeah, okay. Then they have a lending laptop from the uni, but then that becomes kind of complicated because there are not enough of them or something. No, you can't do it in a virtual machine because it's got to be like. Let's see, I'm reading so they can press the board. No, I mean, the whole thing is silly. I mean, it's first of all, what was really nice. Okay, Cambro had a nice exam system, but the thing with the Cambro system is that you can't use that anymore because they've signed some kind of exclusive contract with this company. Listen, I have nothing against this private, whatever, you know. I'm not saying there's anything wrong with that, but no, we're going to do it on paper. I mean, it just, yeah, bypass the whole idea. That's right. I mean, we're gonna do it on paper, and then what that means though is it means that the nature. So you're not going to have any access to a book. So you're going to have to kind of put all the stuff in your head, which is kind of the way I like it, anyways, because I think that having to kind of get all the stuff inside your head. I mean, open book exams are not really good because it's just like, okay, maybe it's more a simulation as to how the real world is because you always have an open book. But it's just that if I force a closed book exam, that means that you have to kind of put the stuff in your head. And if you put it in your head, the idea is maybe it'll stick. So it's going to be a closed book exam. So it's going to be a little different than the recent exams I've given, because back during the COVID era, in the initial COVID era, we actually gave the exams on Cambro. And that was nice because they were digital, but they were also insecure in the sense that it was just all the honor system. We had to go through the honor system. Apparently, in the long run, they want to be able to control it, which I guess makes sense. I mean, honor system. I mean, you guys are all. I think for them, I found that students are very honorable. So I mean, I don't really worry that much about like cheating, but the system needs to make sure that it's. We had Cambro open because in the beginning it was like emergency, but now it's like no, we'll do it as a paper exam. As far as the exam registration, I'm going to bother them again, but the thing is that if you guys bother them, it has a lot more weight, because it's like you guys are. For me, it's like I send a message and then it's like, no, I don't know. I mean, they listen to my messages and all that, but I don't know. I mean, I sent a message, but I haven't gotten a response yet. So if you guys, I think you guys will push the priority up if you guys start saying, where can I register for the exam? I've made it very clear to them it's going to be a paper exam. Okay, anyways, guys, I mean, whatever. Even if this is not, you can't register at all, everything's blocked up and locked up till like the day before the exam. It doesn't matter, because I'll be there in person saying, these students can take the exam. I will never, ever have a student turned away when they show up at the pavilion. All students, I've never, ever had a student of mine. They've said, oh, well, should we turn these people away? I said, absolutely not. Because I always print out many, many extra copies. Now, when we have the actual, I mean, I'll go over the exam when we have the exam. Let's get to the actual content here, and so we can actually cover some, rather than, all right. I guess, I mean, I think the questions are, I think I've answered all the questions in the chat. Send me another chat question if you want to. All right, so now we're going to talk about some real practical stuff in terms of SQL now. And this has to do with views and indexes, and also basically temporary tables, which is something else I want to talk a little bit about. But okay, a view is a relation defined in terms of the stored tables. One second, guys. Hello? Okay, that was not necessary. Okay. All right. So a view is it almost behaves exactly like a relation, like a normal table, but it's kind of derived from the base tables. And so there are two types of views. There's the pure virtual view, which is the classic view. And then there's what's called a materialized view. Let's just look at an example of a view here. So when we go back to like our running example here, the drinking of beers, we can define a view called can drink. And this, of course, pairs a drinker with a beer. And so the idea here is that if a drinker frequents a bar that sells a beer, right? So I frequent, say, Rex, and Rex sells Prips, then I can drink Prips. But if I don't frequent Rex, or I don't frequent any bar that has Prips, then I can't drink Prips. So the way this works then is it basically just gives a definition of this can drink table, if you will, but it's not a table, because it never actually gets filled with anything. What it is, it's basically it's defined as the can drink here is defined as selecting the drinker and the beer, but we're doing a join over the frequents and sells. So the drinker is coming from the frequents, and the sells is coming from, is what the bar sells, and this join here then ties together drinker and beers. So it's from drinker and beer. So if you recall, the sells has a beer, all right, and drinker has and frequents has a drinker. So it's grabbing the drinker from frequents, and it's grabbing the beer from sells, and it's just making sure that they join through. So the way this works actually then was that when you then ask a query, so like select the beers from canned drink where the drinker is Sally. What it does here actually, I mean, this is kind of internally what it's actually doing, is it's going to this canned drink table here, and it's going through and it's expanding it with this definition here. So this definition here winds up being substituted in here. So when you look at the way PostgreSQL or any SQL processor does it, is they do it just by actually taking your query and then substituting in the definitions. So it kind of makes your query a lot more bushy. So so your query actually is involving these two extra tables that are defined, that are in the definition there. So that's what a view does. So a view is just simply a syntactic. It's defining the way that your query, because you're going to use, when you use the view, it defines the way that your query gets expanded out syntactically. All right, and then once it gets expanded out syntactically, then the query itself is only over the true tables, the base tables of the database. So does that make sense to people? I hope it does. So so these are really, really practical. And one of the great practicalities with these is a lot of views will have stuff like functions. And so in other words, instead of like selecting the drinker here, you could have something like where you would basically have you could have an arbitrary function here that would then define the attributes coming in. So you could have something like one view you might have. Let's say you had a table that you had a query that basically had a record of everything that you ate, like the person and what they're eating that day, and what they're eating then has a number of calories, or every food has a number of calories, and I'm eating a certain quantity of each food, and it's happening each day. It's very easy then to define a view that will basically sum up all the calories per day. So you could create a view that basically has the date and then the total number of calories that got summed over the base tables, right? So that's actually a very, very common use case for views, is that you're doing reporting with views, right? So I hope that makes sense to people. And then notice the thing about the view is that it also, is that a view doesn't cause any additional, like nothing's being stored. It's just all syntactic, all right? Now, there's another concept which is called a materialized view. And what a materialized view is, what it does, it actually goes and it builds kind of internal to PostgreSQL, it builds a temporary table, all right? It builds a temporary table so that the access to it, the access to the actual data is it has much better runtime performance, okay? So you might think about this, you might say, well, let's say that I have a view that's supposed to do all this like summing up of the, let's say I'm a company, I sell thousands and thousands of products each day, and I want to have like a tally of how much revenue each product brought in and what store it was at and all that other stuff. So I could define a view that did that. But if I define it as a view and I'm asking a lot of questions over that view, then it's going to be recalculating all those numbers every single time. What might actually make much more sense is that I materialize the view. So I do all the calculations of like the summing up and kind of what stores and the total revenue and all that stuff. I do that inside of a materialized view. And then once per day, I say recalculate the materialized view, and it completely rebuilds those internal temporary tables, if you will. They all get rebuilt. So that's the notion of what a materialized view is. So it just means that it's been kind of it's the same as a view, but it's a materialized view means that it's like actually calculated the view and stored it in temporary tables. And this all happens kind of invisibly to you as the administrator of the database or user. You just kind of declare materialized view. And then once you have the materialized view declared, then you can just use it, and it has much higher performance. Okay, so those are the ideas behind views and materialized views. So you'll find yourself doing a lot of you'll find yourself working with views quite a bit. Now, a couple of points that need to be made about this. One is that there are only some views, not all views, but some views where you define the view, and then when you define the view, you can actually do an update over the view. but in general, you can't. So for instance, let's say that let's look at this guy right here, this canned drink here. So if I say this, if I say, okay, I have this view called canned drink. Now, if I say that Bob can drink Prips, so I try to do an insert into this view of canned drink. Bob can drink Prips. Well, notice how there is, it's ambiguous as to what that means in terms of inserts over the base tables. Because we know that what do we know when we say that, oh, Bob can drink Prips? We know that there's a bar that Bob frequents, and that bar sells Prips. That's what we're saying when we say Bob can drink Prips. But we can't really identify which bar it is. All right, it could be any of the bars that sell Prips. Right, so it's ambiguous. So you can't reflect the update over the view back into the base tables. Right. Now, in certain cases, you can reflect the view back into the base tables. So let's say that I have a view, for instance, where I have employee, they have a persona number, and they have a name, and they have a department, and they also have a salary. Now, I define a view where I'm just basically saying restricted employee. And what that basically does is it creates a view where it's just saying selecting the name, the persona number, and the department, but not the salary of the employee. So this might be a view that we allow for certain people to look at who work in the organization, where we don't want them to see what the salary is of other people working in the organization. So that kind of view, that's a common use case of the view as well, is to kind of have a restricted view, as it were, into the data for the purposes of authorization, who's authorized to see the salaries. But in that case, when we look at that view where we would define the restricted employee, or the employee without salary, we have that view. If we then add an employee to that view, then actually we should be able to reflect that back into the base table, where the salary would equal the value of null, where it's unknown. Okay, so PostgreSQL actually will, if you use PostgreSQL to define views, then it's pretty smart about determining when and when it cannot reflect updates back into the base tables. All right. So in that restricted employee case, I hope that people are following this. In the restricted employee case, PostgreSQL will actually let you do the inserts. It'll have null value as salary if you do that. So that's one thing just to keep in mind with views. That the updates and inserts, those become, they kind of like views either can reflect back to the base tables, or they can't. And when they can't, they restrict the ability to do updates over them. Okay? So PostgreSQL will just simply not allow you to do it. Okay. So that's views. Now, there's another thing I just want to bring up as kind of a typical use case. There's also the notion of what you could call like a temporary or intermediary table. So this actually, in the real world, this is quite often what you want to do when you do stuff like data exchange. So data exchange, I mean, is a multi-billion-dollar industry basically, and what it has to do with either I have a legacy database, or I have a just a different database, and I want to move data from one database or one schema into another. Right? This happens all the time. I'm sure you can imagine that. Okay, for instance, it might be that we have an old we're using an old system at some workplace, and we want to basically transfer over to the new system. And so what you need to do then is you need to define the tables in the new system, and then what you wind up doing is you wind up doing something similar to Materialize. But what you do is you wind up saying select into. So if you're insert select into. So if you recall, when we talk about inserts, you can do this basically select, and then you do it like over the base tables. You do like some complicated query, and then you say into, and then you have the name of the new table you define. And what that does, what that achieves, it achieves moving the data from one of the tables, reformatting it, and then populating another table. It's very, very common, a very, very common use case. I mean, there's lots of different people who are doing lots of different work when it comes to this kind of stuff. I would draw you guys' attention to a tool called DBT. So it's a very active community around. It's called Database Build Tool. It was started by this company called Fishtown Analytics, and now it's called DBT Labs. So they changed the name, and they got a whole bunch of funding. So if you go to the DBT database tool, or sorry, database build tool, data build tool, DBT, database build tool, yeah, DBT. Now, if you look at that, you'll see kind of a lot of what's going on. Really some current work in this area. So yeah, so there's a lot of activity there. I would for people who are interested, I would point them toward that. All right, so that kind of covers like the three options you have. You have views, you have materialized views, and then you just have the idea of having temporary tables that you select into. All right. The third one, people don't want to do. They're kind of anti that, but in practicality, that's actually what you do a lot of times because it's really, there are a lot of real benefits to that. One of the main benefits to that is that you don't have to do. I mean, you declare the tables, and then when you do the select into, you can be really. Let's see, how would I put it this way? I would say that once you have the tables defined, then the select intos. I mean, it's very, very flexible in terms of how you do it. But you have to. The point is that you have to kind of. There's a notion when you do that of what's called idempotency. And idempotency, I don't know if you guys remember what idempotent means. Okay, views are idempotent, and materialized views are idempotent. So what that means, it means that, well, you could apply them any number of times and you always get the same thing. Building temporary tables and doing select intos is not in general idempotent. So if you do it once and then you do it again, you get even more answers. And a lot of times that's not what you want. What you want is a notion of idempotency. And what DBT does is it ensures those kind of idempotencies by arranging the whole build as a DAG, a directed acyclic graph. So there's a lot of stuff going on with that kind of stuff. It also DBT also adds in kind of a Git type approach to kind of data builds, so that you have kind of a full record, a full history, and you can kind of treat it like a Git repository. So it's got some of that support as well. So as you can imagine, that's quite practical. All right, all right. So that was kind of views, materialized views, and temporary tables. So now let's talk now about indices or indexes. I tend to kind of go toward just the kind of English kind of rules in terms of plurals. Indices is kind of correct, but I'm kind of indexes. I'll call them indexes. Just like I say schemas, it should be schemata, but schemas. I try to keep everything really kind of basic. I mean, I suppose you say consortium, consortia. So consortia is a plural of consortium. I can hear myself saying consortiums, which of course people would think I'm an idiot for doing that. But in general, I like to kind of like get rid of the old Latin and Greek roots of the language and kind of just make it all English in terms of the plurals. I'm one for kind of standardization. All right, indexes. All right. So indexes are basically something kind of like the following. What you wind up doing is you can, in PostgreSQL, something like say create index beer in. So you have to give it a name, beer in on the beer's manufacturer. So what this basically means, is it someone? What this means is it means that what you're doing is you're building, excuse me, you're having the database build like a structure on the side to get really heavy duty speed ups in terms of query processing. Okay, so without being able to create indexes, databases would be really impractical because it would be doing a lot of like linear searches. One thing you might say is this: is that indexes are already being built for your primary keys. So when I have a Person number, so think of it this way: when I have a Person number, so let's say I declare a table of people, and it has as the primary key it has Person number, right? And that Person, let's just say that I have a table that has three attributes. It has the person number, it has the name of the person, it has the city they live in, and then let me put in a fourth one, it has their gender. All right. So So again, I'm defining a table called person. It has a pnum, which is the person number. It has a name. It has the city they live in, and it has their gender. Okay. Now, when I declare pnum to be primary key, then PostgreSQL is already automatically building an index for pnum, for the pnum attribute. So then if I say, I fill it up with like 10 million people, I fill all full Sweden gets put into that table. By the way, would that table, could we populate that table on our laptop for all of Sweden? The answer is obviously yes. That is not much data at all, right? That's pretty peanut in terms of the size of data. Is that, what is it like? I mean, you can just do the calculation. I mean, that's just like, that's nothing. All right. Anyways, let's say we did that, right? But then I say, give me the person with the person number 7891. No, I'm sorry, that's not possible. 7804 20-1141. Okay. Now, because it had built an index on person number, it winds up doing it's looking for that one particular person, right? It does not scan through all 10 million records. It goes to what's called a B plus tree. So in PostgreSQL, they're all based on what are called a B plus tree, which is a generalization of a binary tree. And so what winds up happening is we wind up being able to locate the actual spot in the database. We're able to locate that in something like 10 million log, basically this, log base something like 200 of 10 million, right? So it's not log base 2. It's not like a binary. It's not a binary tree. It's much bushier than a binary tree. So we're talking about, let's say, take something like log base 200 of 10 million. And if you do that calculation of what log base, it's like 3 or 4 searches we have to do in the tree until we find the spot. So it's almost like constant time. Right? So if we didn't have an index built over the person number, then it would have to kind of go all the way through the whole thing in a really stupid way. It would have to kind of go through the whole database looking for that person, a particular person number. So primary keys are already getting indexes. It's already happening. But let's say I also want to have an index. So in this case here, we did manufacturing on the beer, on beer. So it's like, who's the manufacturer of the beer? But in the example I was developing a second ago, we could do basically, let's create an index on the city the person is in, right? So that if I want to say something like, give me how many people live in Umeå, all right, select star from person where city equals Umeå. If I build an index on person over city, I'm going to get tremendous speed ups when I do that calculate, when I do that query, right? Because it's going to be able to just to locate all the records where they're in Umeå, and it's just going to be able to add those up, right? The thing about indexes is that all right, but then there's another one. What if I said create an index on gender? That one actually won't be very helpful since there are presumably 2 or maybe 3 or maybe 4 genders. I don't know how many genders there are, but I mean, it depends on how you represent gender. But if there are I mean, there's going to be a bounded number of genders. So it's not going to be so useful to actually build an index on it because it won't be that discerning. We'll come to that later. The advanced course talks a bit more about those kind of low cardinality indexes over low cardinality attributes. Like a gender is a low cardinality attribute because there's not that many different types of them. City has a much higher cardinality, so you might have like 700, 800 cities, and that's going to form a reasonable partition of the people in the database. But we also we could build an index on the person's name as well, right? So we could say basically, give me the people who have a particular name. If we have an index built there, we're going to get a major speed up. Another thing also, if you look right here, you could also build indexes on pairs of attributes, right? So you can have really, really sophisticated ways in which you do bringing together of. So a query that's basically going to have set is going to be looking for the, you know, it's going to have in it, it's going to have a bar and a beer, like asking, does this bar sell this beer? When it has that, it can take advantage of this index here, which would allow for extreme amounts of speed up for that particular type of query. So you build indexes, you can build a whole ton of indexes, and they're all giving, they're basically giving you different access paths into the data that would then give you tremendous speed ups. Okay, so let's see here. This is like a simple example here, where if we have, this is just like in the slides here, just shows an example where if you wind up having those indexes built, you'll see that it actually uses them. Let me just see here, tuning advisors. Yeah. Okay. So there's a maybe I'll do this in a separate screen. One second. Well, no, I can do it this way. If you guys can see it, I'm sharing the screen. So let me see here. I'll just say Manny. All right. So if I say something like select and then blah, 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 whatever the query is, if you out front of that, you say explain, analyze. So if you put this in front of your query, explain, analyze, it will actually show you what indexes are being used when it's evaluating the query. Okay. So this is how you actually, so if you create a bunch of indexes and then you want to put queries in, you say explain, analyze in front of them, then you get to see kind of how it's actually figuring out how to use the indexes in the answering of that query. So what you do when we get to something like database tuning, I mean, this is like kind of, this is big money because, a lot of times what you'll have some people, they build a gigantic database. And as we all know, if that database is the least bit sluggish when people are trying to access it, if you have end users trying to access it, and it takes like a half a second is terrible. Any kind of delay at all is absolutely, for interactive processing, any type of noticeable delay to a human being is just, I mean, it's unacceptable. Things need to be absolutely immediate. So you'll find that you really got to work on like getting interactive performance down to very much sub-second. And if you've got a lot of users that are using the database simultaneously and you have a lot of data, this becomes difficult. So a lot of times, so this is your intuition here. So the thing about creating indices, so you wind up creating a whole bunch of indices. One level, I mean, one person might think, well, why don't I just build all potential indexes and all potential index combinations? And the problem with that is that it would slow down. You have to maintain every index you build, you need to maintain. So what that means then is it means that if you wind up building just a ton of indexes, it's going to take up more space, but that's not really the more serious problem. The more serious problem is if you're making a lot of modifications to the data, you have to maintain those indexes. So it'll really slow down your inserts, updates, and delete queries. So because every time you do an insert, update, and delete, it's going to have to go in and change all the affected indexes. Okay. So there's kind of a natural trade-off then that happens based on that. So database tuning is really a lot of times about like, figuring out what the proper mix of indexes that you should have are. And what this means is it means that this is always relative to a certain kind of load of queries. So if the queries that are coming in have a certain distribution to them, so there's a certain set of there's a certain, like we don't do any inserts, for instance, then okay, well then that would make it so we can have more indexes. But let's say we have 20% our database modifications, where you're changing it to seeding, or you're changing something, or you're changing it. The other ones are like questions that are asking for like particular availability on flights or something. The other one is asking about how many the other one's an analytic question about how filled are the flights, these kind of things. So you might have like a mix of queries, and you might have views that are also using those base tables. which have indexes built over them. So you have this very kind of complicated environment in which the database is actually being used, and you'll get better performance based on which indexes you do or do not build. Right? So this winds up becoming kind of a big task for people to deal with. So again, the company wants to really speed up access to the database. Sometimes if it's too slow, then it's not even useful. I mean, if the database gets too big and indexes are have a lot of problems with them, if basically the access winds up taking way too long, then the database is kind of rendered inoperable. So a lot of times these kind of database tuning jobs are a lot of times emergency operations. And there's a lot of things that are involved with those things. There's like maybe you would actually want to go in and completely rebuild the indexes. So you want to re-index. So delete all the indexes and then completely rebuild. Sometimes you want to just have some operations where at a certain time of the day you optimize the indexes, in the rebuild. And then of course there's always the decision of what indexes are actually there in the first place. So it's a gigantic kind of optimization problem. There's been some attempts to kind of automate that, but it's really quite difficult to automate. This is usually it's kind of a black art about how you actually set up the indexes and you set up the kind of the policies around like day-to-day operations. But as you can imagine, since performance is so important, it winds up becoming it's a very highly, if you get good at that skill, it pays very well. It's a very highly paid skill to go in and do database tuning. Right. So yeah. So anyways, that I think covers indexes for us. So if there's any questions, just put them in the chat. By the way, in the chat, and then we're going to go over transactions. By the way, in the chat, it looks as if the registration for the exam is now open on Student Bevin, so that's good. So register because they want to have some idea of how many people are coming. I guess if you don't register, you're supposed to wait like 15 minutes or something, or a half hour or something crazy. So it's a good idea for everybody. Everybody should go register today if you can. Okay. All right, so now let's move on to the other topic we're going to cover today, and that is transactions. Okay, so transactions. So I mean, it shouldn't be any big surprise, but so normally the databases are being accessed by many users or processes at the same time. So both queries and modifications. So read queries and write queries, basically. I mean, normally, if you think about like an operating system, you can have many different people and processes accessing a file system. And usually the way that works is that files get write locked. And then what happens is if you try to write something that somebody else has a write lock on, it won't let you, right? It'll block you. So in databases, it's a little bit more complicated. So what we want to do is we want to look at some kind of really so let's just say for now, let's say that we're not going to have anything special. We're just going to allow for multiple people to use the database concurrently. So that is that two people can just wind up using the database with no restrictions whatsoever on what they do. So this would be like an example of a very bad interaction. This is what's called the lost update problem. And so this is very problematic. So let's say that, for instance, you have a joint bank account and you and your partner both take out $100 from ATMs at about the same time. Right? So the database better make sure that one account, one deduction doesn't get lost. So for instance, let's say that, let's see here. So let's just work this example here. All right, I'm one transaction, and then my partner is another transaction. Well, the first thing I do is I check to see, is there more than $100 in the account? Let's say that there are $300 in the account. All right. So I check and I read. I say, okay, oh, there's $300. Good. Now I'll take out 100 and I will update the balance back to 200. Okay. Now at the same time, my partner is doing the same thing. And so what she does is she'll like look and see like, okay, well, she does the same thing. So we both, let's say we're both like, I read it's 300, but then immediately she reads and it's 300. Then I take out $100 and I write back $200 as my balance. And then, but she just read 300, so she takes out 100, and then she'll write 200 back as the balance as well. So we both got $100, and now the account was 300, and now it's 200. So one of our updates got lost, right? One of our deductions of $100 got lost. Okay, in this case, it worked out for us. We got extra $100, but the bank won't like that because money was not money was somehow lost, or money was not conserved. Money's like energy, right? I mean, the same amount of money should always, it should all sum up to the same amount. So that would be a bad case of the database really messing up and us having a lost update. All right. So that is a no-go, that we can't allow that to happen. Compare like with an operating system, a lot of times you can have it so that like, well, you're right, you both open a file, one person does a bunch of writes to it, then they write it out to disk, and then maybe if there's not much control over it, another person makes their changes and they overwrite the other ones, and they clobber the other ones changes. So that would be bad. So what transactions do in databases is it's a way to kind of manage this. So it's a way to kind of group things together and manage them so that whatever happens, it'll actually wind up making sense. So in the case of me and my partner, both like, seeing, like, think of it this way. I see that there's $300 in the account. She sees the $300 in the account. I take out $100. She tries to take out $100, but the database system says, no, you got to restart your transaction. She says, oh, okay, whatever. She restarts the transaction, and she now sees that there's $200 in the account. She takes out $100, and then now there's $100 left. Okay, so then that makes sense because I got $100, she got $100. The account went from 300 down to 100. But notice how there was an intervening step there where her initial transaction that she started got aborted. So that, or rolled back. I mean, we don't probably, I should probably use the term rolled back. Okay. But those are they're synonymous in database transactions, rolling back or aborted. So the point is that her initial transaction was not allowed to go through. Right? It was blocked because something weird happened with its interaction with my transaction. Right? And that's exactly what happens in transaction processing. This is exactly what it winds up doing. So it winds up having kind of there's a method and there's a theory that kind of guides how this winds up being controlled in the database. Okay, so a lot of times you guys have probably heard like this notion of like transactions being characterized as acid transactions. Okay, you'll hear this a lot. So acid transactions are atomic, all right? And the atomic means that the transaction either goes all the way through, or either everything's done in the transaction or nothing is done in the transaction. All right, so it's like, excuse me, you can come up with more complicated examples where we're transferring money between accounts. So like I take $100 from account A and I put $100 into account B. All right. And now imagine a whole bunch of people doing that, trying to do that simultaneously. I might be able to take $100 from account A, but then when I try to add it to B, the database system might say, no, you can't do this. You're going to be rolled back. And if you want to do that, you need to restart and kind of read because somebody else, you were being intertwined with somebody else. So you have to restart. So if that has to happen, if I have to be restarted, then that me taking that initial $100 from account A has to be rolled back. All right. So transactions either go all the way through or they don't go through at all. Either they're rolled back or they're committed, one or the other. Right. And so there is no kind of partiality about how the transactions go through. All right. That's the A in ACID for atomic. Consistent means that if there are like things like you have rules that are guided in the database, like what needs to be true, like foreign key constraints, primary key constraints, of course, but you can have any arbitrary set of other constraints. These must be at every point, at every potential state of the database. Like so, when these transactions go through, you'll hop from one point to another point. The database needs to be consistent at the endpoints, right? So you'll always have kind of like one version of what the database is at any particular moment in time, and it has to maintain consistency. It has to be consistent. Usually the C1 doesn't really enter into like our discussions at this point. But if we deal with stuff, consistency has to do with more complicated constraints that we really haven't covered. Okay, now isolated. Now this is really kind of something that you aim for, and this is the one spot that kind of wiggles a little bit. So the I in ACID, you can go into different isolation levels, but the pure notion of what isolated means is that it gives you the impression that you are the only user of the database. Right? That's what the I in isolated means. You don't you feel like maybe there's like 1,000 people accessing the database simultaneously, but you're given the impression that you're the only user. Right? So you feel isolated from others. So you don't see things like changing around a lot. Right? When you look at the database, it's like the same. It's always consistent. Now, of course, that's impossible to maintain purely. Sometimes your isolation gets interrupted in a very rude way by your transaction being rolled back. All right. So usually what will happen is your isolation gets punctured or gets retracted when you actually have to have your transaction rolled back. But otherwise, you're given this impression that you're the one and only one user of the database. And then finally, we have the D, which is durable. And what this means is it means that if I commit, if the transaction commits, so for instance, if I transfer $100 from account A to account B, and it goes through and it says, okay, transaction committed, I am certain that that actually has been reflected in the database. And it won't be one of these things where like 2 minutes later, that gets retracted because of some strange interaction with other transactions. Once it's committed, it's durable, all right? And that also means durability also has to do with the notion of write-ahead logging. It has to do with the fact that it's, even if the power goes off, right, that it's durable, that it will survive a crash and it will not be rolled back. Like after there's a notion of what's called a cascading rollback. That is that, and no one ever accepts this. It's completely unacceptable. But the idea would basically be because of some strange interactions, I get my transaction goes through, but because of some strange interactions and what I was writing stuff out and somebody else was reading it, whatever it might be, there is a certain kind of case that if you don't guard for it, this is internal to the database system, that it actually would require that the transaction that I ran that was committed needs to get rolled back, and that's completely unacceptable because I've already been told that the transaction has committed. So D is very, very important to preserve. So the durability. So once I've been informed that the transaction is committed, then it'll stick. Okay. So weaker forms are going to be the isolation. We'll see how that goes. So let's talk about a little bit practically. How do you actually get transactions to work? Like how do you actually do them? So what you do is you start out in SQL. You just have a begin and then a semicolon. When you type that into PostgreSQL, that starts a transaction. Okay. So if you want to play around with transactions, what you can do is you can open two windows into your database. Right. So you do PSQL and you connect it to SQL on two windows into the same database. In one of the windows, you say begin semicolon. Right. Okay. So you're starting a transaction there. And then on the other window, you say begin semicolon. Okay, now you're starting a transaction there. Now you can do reads and writes and you can do whatever you want. And each of those windows can feel isolated. But if you do you do select, so you're doing reads, and then you're doing updates or you're doing inserts, you're doing deletes or whatever, you're doing writes. It may be that in one of those windows, after you do something in the other window, that one window basically says, whoops, roll back. You got to restart. Okay, and that's the case in which the concurrency controller decides that no, this is impossible to let both of you continue on with, and we want to keep the database in a consistent state. So we have one of the transactions needs to get rolled back. So you can actually do that just by opening two windows, to the same database. And so you can, and in each window say begin, right? Now, you can go and you do your reads, which are select queries, and you do your writes, which are update, delete, or insert queries. And then at the end, what you do is you say commit subcolon. Okay, when you do that, then you're doing the commit of that transaction into the database. Now, at that point, it's either going to accept your commit, which is in which case, because of durability, it's done, or it's going to roll you back and tell you that no, your transaction can't go through. You got to restart completely. Okay, so that's what happens when you do the commit. It may or may not work, right, depending on what other transactions have done. Rollback. If you can also type in the command rollback or abort, and that will actually just quit the transaction, and it'll be as if it never started. And then, of course, if you have like some kind of programming errors, if you have any kind of SQL errors, those typically will abort the transaction. Okay, so now the fact is that this stuff is usually done through some kind of UI. So what you wind up having is you have some kind of middleware and like a Python, like you have a Python middleware, and it's talking to the database. And what it does is it's in a programmatic sense. It basically starts and it starts transactions and commits transactions. Okay, so there are programming language calls that do the starting and committing transactions, and so the programming language calls into this kind of stuff is what is a lot of times what's really doing the kind of controlling the transactions. So for instance, when you go, I'm not sure how many of you guys have had the experience, but have you ever gone to like a travel site and you or like an airline site, and you're sitting there, and then you're buying your ticket, and then you have you can pick your seat assignment, right? And you say, oh, that seat looked really good right there, like 10A. Oh, that's a perfect seat. And it's sitting there. It's like one of the available ones right on the screen. And you go with your mouse pointer and you click on that thing, because that's the seat you want. But then something weird happens. It kind of blinks a little bit, and then next thing you know, it's like sends you back to like the earlier screen, and then you click on seat assignments again, and then that 10A is not even available anymore, right? So that's actually you and somebody else beat you to it. Now they won't tell you that, they're not going to give you an error message saying that like, oh, somebody else beat, because they don't want to confess the fact that they're just going to send you back into some other prior state of the UI interaction. And then you're going to come back in there and you're going to see that it's gone then. And then you're going to kind of scratch your head and say, well, all right, I'll take 8A instead. All right. But this is exactly what's happening. I mean, is that the middleware that's controlling like the seat assignments on the airline's website or whatever for that flight, it is doing transaction processing, because it can't assign. I mean, it flashes up. I mean, you notice there's a moment there where it flashes up to 2 people around the world the availability of seat 10A. One person grabs it, and it's not going to then, like, based on that person grabbing it, it's not going to then kind of send a message back to your browser and update the selection. It's not going to do that. It's just going to leave the selection as it is. But when you try to click on that new one that was then already occupied, it's going to go into some kind of weird state in the middleware that's going to cause it to kind of just back out and then force you to go back into that seat selection screen again, right? So I'm not sure. I mean, people can like reflect. Have you ever experienced something kind of like that? All right. Well, then you've experienced transaction processing. Okay, so let's look at this example here just to kind of get. I mean, transaction processing. I mean, it's kind of complicated under the hood, but I mean, there's an intuition about kind of how it is, and I'm trying to kind of give you the intuition in this lecture. So let's say that we assume that the usual sells, so a bar is selling a beer at a price. And suppose that Joe's bar sells only Bud for $2.50 and Miller for $3. Right? Sally's querying the sells for the highest and lowest price charges. I'm sorry, lowest price Joe charges. Okay, so so Joe is only selling Bud for $2.50 and Miller for $3. Okay, so the highest and lowest then is $3 and $2.50. But Joe decides to stop selling Bud and Miller, but then will only sell Heineken at $3.50. So Joe is actually, there's two transactions here. There's the initial state of the tables, of course, which is that Joe's is selling Bud for $2.50 and Miller for $3. Sally wants to know what is the highest and lowest prices that Joe charges. But then Joe also is going to stop selling Bud and Miller. He's going to stop selling both those beers, but then only sell Heineken at $3.50. All right. So let's look at how this can interact. All right. So Sally's program. So Sally's program is give me the max price that Joe sells a bar for, and give me the min price that Joe sells a bar for. Okay. Now Joe's program is delete all the selling that he's doing. So, Bud and the earlier beers get deleted. And then insert just that he's selling Heineken at $3.50. Okay, so let's interleave these statements and see what happens. So if we do the following execution order, where first Sally says, what's the max? And she gets back $3, of course. And then Joe does the delete and the insert where he puts in Heineken. And then Sally asks, what's the min? And she gets $3.50. So notice that even here, max is less than min. All right, so which makes no sense whatsoever. So this particular interleaving of operations leads to some a very strange read property. Okay, so we have to basically block that. All right, so if we don't do any transactions at all, so you can always run without transactions by just running everything as a separate SQL. So if we did that, if we just kind of very naive in how we implement this, we wind up with a very strange result, unintended result. So if we group Sally's statements into a transaction where she's asking for max and min, that's one transaction. So, and then Joe's is also going to be one transaction. Then basically what that means is it means that either the only allowable ways that this is going to go through, if they're transactions, is that Joe is going to run either Sally. So basically, there's two possible schedules that would make sense in this case here. If we basically say Sally's program is a transaction, we would basically say, okay, if we run Sally's program first, then we're going to get $2.50. I'm sorry, we're going to get $3 for max, and we're going to get $2.50 for min, which makes sense in that particular instance. And then if we run Joe's program, we're going to then wind up just getting the Heineken's being sold for $3.50. Both of those make sense because Sally's program reported the correct answer before Joe's program ran. So the information Sally got back was correct at that particular moment. Then Joe's program ran, and maybe it was changed. Another way this could run is if Joe's program runs first. All right, so then basically, okay, it's $3.50. There's only Heineken being sold. And then Sally's program runs, okay, $3.50 and $3.50. That's consistent as well. So what this shows, it shows that that when you talk about transactions, so if what you wind up talking about is wind up talking about serial schedules. And if I have, let's say that we're all isolated here, and let's say 10 of you people all have 10 separate transactions you want to do over the database. Okay. Now I can make sure everything is consistent by doing the following. Okay, 10 of you want to run the database. 10 of you want to make changes to the database. Okay. So what I say basically is I say, all right, I'm going to put those 10 people who want to make changes to the database. I'm just going to line you up in order. And I'm going to say, person number 1, do everything you want. Okay. Then the person number 1 is done. Then person number 2 can go. 3, 4. Okay, so some order. There are 10 factorial number of orderings over those 10 people, and all of them are legitimate, right? Because what I'm doing is I'm basically just putting one giant lock over the database and saying person 1 gets to go and finish, person 2 gets to go and finish, 3 gets to go and finish. There will be no weird intertwining of transactions, okay? So that is what is actually happening when I look at this Joe and Sally's programs. I'm saying there's 2 orderings. Sally goes first or Joe goes first, or Joe goes first and Sally goes first. Right? Both of those make sense. Those are both what are called serial schedules because they make sense. No one can complain about those There's a difference in, of course, in the results, but they're both consistent. But as we showed in this example here, if we allow them to intertwine, we can get a very, very weird case where there's no where the max is 3 and the min is 350, and there's no possible way that would ever happen in the that is not in any way consistent. That is a strange interleaving. That is a weird artifact of the particular way these things kind of blended together, right? So that does not correspond. That result does not correspond to any of the serial schedules where I had either Joe goes first and then Sally, or Sally goes first and then Joe. So this is kind of illegal. And this needs to be precluded. All right. So what this basically comes down to is it comes down to what's called serializability. So that is the schedule equivalent to some serial schedule? Now let's go back to the example where I say 10 of you, we have a database where we have like accounts and we have amounts of money and whatever it might be. And I say that I line up 10 of you and I just say that, now that's a serial schedule. So I let the first person go to completion and the second person, third person, etc. That will make sense. But let's say that the 8th person and the 9th person, they're touching different accounts. The 8th person is touching account 44 and account 79, and the 9th person is touching account 14 and account 7. They're not touching each other in any way. So actually, we should, for the purposes of performance, we should let the user 8 and user 9 interleave in any possible way they want. It won't make a difference. It will always be equivalent to some serial schedule. All right. So that's the notion of serializable. So what you do in database processors, you have an isolation level called serial. It's the best one. It's called serializable. And when you declare your transactions as serializable, then what it does then, it means that that whatever gets done, if it goes through a serializable, then whatever gets done is equivalent to some serial schedule, to some just lining up of the transactions in order. It's equivalent to one of those, but it's got better performance because it allows for interleaving of statements. And of course, this makes perfect sense when the things that the transactions are touching are completely independent from one another. All right. So databases are very smart about that. So it's a trade-off of performance. So if I say, oh, this is scary stuff, I don't want to allow for any weird intertwining of transactions. So therefore, what I'm going to do is I'm just going to line all the transactions up and say, transaction 1, you go first, then 2, then I put an order on like that. But the thing about that is that it has very bad performance, because in my performance, because transaction number 7, who's completely independent of everybody else, could actually run at any time, right? So a smart processor would allow for transaction number 7 just to kind of come and run and intertwine with everybody else, because they're not touching anything that's related. All right. So if I can have a smarter way of doing it, then I can get much better throughput, much better performance, because then transaction 7 can just run, right, without being waiting for transaction 1 through 6 to complete. Right. And of course, this is even worse if we're talking about interactive transactions. So there's basically 2 types of transactions. An interactive transaction is one where you have the human being in the loop who's deciding how the transaction is going to proceed. They do some reading, then they kind of like think about stuff, and then they do some writing. Okay. A transaction like that, all right, if you have 10 people lined up and they're all interactive, then the 7th person might have to wait a long, long time before they can actually run, because they have 6 other people in front of them who are sitting there and kind of, trying to think about what they really want, etc. All right. So there are programmatic transactions which are completely automated. All right. Now they could what they do is, those are actually, it's a different kind of beast, but they're still the same theory. But basically, what those things do is they run, and if they can't run and they get aborted, they just rerun. Right? It's always kind of built in. The definition of how they're supposed to operate is always built in. So then in principle, I guess you could line those up in this way, but even there, it would be bad performance. So I hope that people understand that internally, you want to have a controller that will that the outcome winds up being a serial schedule, but you don't want to have a controller that's so conservative that it just enforces serial schedules, because that would be impractical. So that's kind of the name of the game in transactions. All right, so let's look at another problem that can happen. This is a very, very serious problem. It's called the dirty read. So let's see. Suppose Joe says delete and then insert, not as a transaction, but after executing these statements. Okay. Yeah. So let's assume this. Let's assume that what happens. Okay, Sally. Let's assume here that basically what the following happens: that Joe executes his deletion of the beers that he's selling, and then he inserts Heineken. All right, and then he kind of thinks about it before he types in commit, and he says, actually, no, I don't want to do that. I want to keep the way I had it before. So he aborts or rolls back his transaction. Now, let's say that Sally, right after that Joe had done his insert here, let's say that Sally executes her statements and finds out that and this is before that Joe's rolled back, and only Heineken is in there now. And Sally looks and sees that well, Joe sells the min and max are 350 because there's only Heineken in there, right? And now based on that, okay, now Sally's done with her read and she's done her analysis of the database, and then based on that, she makes a decision about what bar to go to or not go to, what it might be. Okay, so she's committed hers because she did the read thing. She's done with her transaction, and she's going to make a real world decision based on the results that she got back. Okay. Now, maybe in fact Sally goes on and then she maybe inserts something else in some other tables based on what she read with this 350. She actually has a table called bars to visit, and only if the min is under $3 does she put less than or equal to $3 does she put a bar into that table. Okay, let's assume that Sally does that. So Sally does a write as well. Okay, and then Sally commits. Right, great. But after she commits, then she says, fine, great. Then Joe rolls back his transaction. So whatever Sally read was dirty. It was a dirty read. Okay, it was dirty data. It made it I mean, because it got rolled back, so it was dirty. Now Sally had, based on that, had gone through and committed and added some other table tuples to a will visit table. Maybe another guy, Sam, runs his transaction based on what Sally had wrote in that will visit table. And then maybe even after Sam, there's a guy named Greg who runs his process. All right. So strictly speaking, when Joe rolls back his transaction, we should have a cascading rollback that invalidates what Sally wrote, and then what Greg wrote, and then what Sally wrote, what Sam wrote, and what Greg wrote. Okay, so that's the exact case of a cascading rollback, and this goes. Which of the ACID properties does this strike against? It strikes against the D for durability. So this is completely unacceptable. It's completely unacceptable because you had Joe did some stuff, Sally based all her decisions on that and committed, and then Sam and Greg did further things based on that. But then lo and behold, Joe rolled back what he initially did. So this is completely unacceptable. And no matter what, we absolutely cannot tolerate this kind of thing to happen in our transaction processor. Okay. So, that's the example of a dirty read. Right. So the lost update and the dirty read are the two really kind of fundamentally bad things that can happen if you don't do transaction processing. Okay, so the solution, of course, is to basically say that Sally can only read committed data. All right. So when Sally, basically what happens here is that when Sally does this read, Joe hasn't committed his reads yet. I'm sorry, he hasn't committed his writes yet. So Sally can only read committed writes, right? So Sally can only read what Joe has done this after Joe actually commits the transaction, right? And that's actually that brings up a transaction isolation level of what's called read committed, and we'll see that come up in a second. This read committed. Okay, so isolation levels. So whatever isolation levels we pick, we have to exclude the lost update and the dirty read. All right. So the best isolation level of all is one called serializable. Okay. So serializable will always force. I mean, generally speaking, they always say that you should. There's like a saying in databases that says this. It says that any isolation level other than serializable is the human mind is unable to comprehend any isolation level other than serializable, because all the other ones have really, really weird kind of cases that can happen. All right. So in general, it's almost like you can almost like take this to the bank, and literally to the bank, and say that you should always run you should always run under serializable isolation level, right? So there's a kind of a famous story now, or infamous, if you will, of a so these are the ones. These are really the ones that you can pick between in PostgreSQL. It's a long story. When we go to transaction processing, if you take the advanced database course, we're really going to go through this in kind of gory detail about how this really happens in PostgreSQL. But consider that you essentially you have three different ways you can run transactions in PostgreSQL. You can set serializable, or you can set read committed. All right. The read commit, you need to set read committed, and that will block the dirty read. All right. Serializable, and also it'll block, for what it's worth, it blocks the lost update as well. But if you run under read committed, so there was a Bitcoin exchange that was running a database system, and they left the transaction level as what was default, which was read committed. And then based on this, somebody was able to bankrupt them. They were, and in the advanced database course, we'll actually show the exact example that we can use. But under read committed, you can allow for a really strange. You can kind of concoct a particular schedule that what it would do is basically the following. It would basically say, if I have two accounts on the Bitcoin exchange, and you're running under read committed, I can send in 1,000 transactions that transfer one Bitcoin from one account to the other. And then what winds up happening when you push it all the way through under read committed is that let's say I have one Bitcoin in account A and I have 0 account in account B. I can push through 1,000 transactions that transfer one Bitcoin from A to B. All right. If it's under read committed, I can put 1,000 of those things in, and what will happen is that account A will wind up going down to minus 1,000, and account B will go up to plus 1,001, right? And that's exactly what happened. That's exactly how they did it. So they were actually able to bankrupt this Bitcoin exchange because the Bitcoin exchange defaulted their database system to read committed. Okay, had they gone to serializable, that would not have been allowed. So in general, you want to go to serializable. But you have three basic options here in practice: serializable, read committed, or no transaction processing whatsoever. Under the no whatsoever, you get really good performance, but you can have a lost update, the dirty read, you can have the whole set of problems. Under read committed, you can still have a lot of problems, but it's very hard to kind of get an intuition about what problems they are. But under serializable, you will only accept serial schedules. Okay, so generally speaking, you want to do serializable and isolation. So I think I already went over the serial transactions here. Read committed basically says that what you do is that you so under read committed, so the thing about read committed, it might be this. If I'm running under read committed, let's say that all of our transactions are running under read committed, then I start my transaction, I read the value of X, and it equals 10. In the meantime, another transaction starts, and it changes the value of X to 11, all right, and commits. Now inside my transaction, I can read X again, and now it's changed to 11, right? So I'm not really isolated because things can change underneath me as long as they're being committed. Right? That's kind of what's happening under read committed. So under that circumstance, I'm not, again, it's not really a full sense of isolation. Now, under serializable, basically what will happen is that it's impossible for me for when I do a read at the beginning of my transaction, like I read X in the beginning of my transaction, and I do some work, and I read X again. X will always be the value that it was when I started my transaction. That you'll get that under serializable. All right. So again, you get a much more solid sense of isolation under serializable. The only problem is that you might get rolled back, so you're not completely isolated. Okay. So that's that. Okay. So what I've tried to do here is I've just tried to kind of build up some intuition around transaction processing. When you read the book, it'll talk about these as being legitimate isolation levels. So like repeatable read. So there's a notion of what's called a phantom. I don't really want you guys to there's read uncommitted, which is basically allowing for dirty reads. There's read committed, which excludes dirty reads. There's repeatable read, which basically means that you always get the same result, but you might get additional things put in. So that has to do with like phantoms. These are all just historic now because these this serialization repeatable read, this serialization repeatable read and read uncommitted for that matter, those are all basically an artifact of an old algorithm called single value concurrency control, which databases used to be built upon, which were all basically lock based. But modern databases, almost all modern databases are using multi-value concurrency control, where they're doing, it's a completely different type of algorithm that's operating under the hood to do transaction processing. And that basically only allows serializable and recommitted to make sense, plus some additional ones, which again, are beyond the scope of this course. So really all I want you guys to focus on are recommitted and serializable when you do the readings. So again, the book is generally, most textbooks will do this. So they'll just kind of present the old fashioned kind of notions of kind of lock-based single value concurrency control when they talk about the transaction level. But those are really antiquated now with multi-value concurrency control. So so do the readings, but then just pay special attention to serializable and read committed. Okay, so that's transaction processing. You're going to have to go to the book for this as well. I mean, I'm not sure how much you guys got out of this. Transaction processing is one of those kind of it's one of those kind of complicated areas in databases that takes probably a couple of reads to kind of have it click in your head. So don't feel bad if you're not quite getting all of this. It is complicated. Transaction processing is quite complicated. And in fact, this whole notion of like, I mean, this again, I mean, talk about the third Turing Award. Okay, so database. This course touches on three big awards. One is like Codd's tuple calculus and relational algebra. The other one was the ER diagram of Chen. And then Tim Gray's concurrent like transaction processing, where the abstraction of reads and writes and the grouping of transactions and this notion of serializability, all that stuff, that also become the basis of another major award in computer science. So these are really kind of fundamental concepts that are kind of coming through on the database from the database world. Again, in the advanced class, you know, if you're interested, and I think it is quite interesting. Transaction processing is quite deep and interesting. We're going to cover it in a lot more detail there, but I just wanted to kind of give you guys a taste and kind of some sense of what's going on with that today. So yeah, and I welcome you guys to kind of go and kind of play around with it. You can, it's very easy to set these things up and kind of see how they work over PostgreSQL. But yeah, so on the exam, we're not going to probably have very much. I mean, I'll look at you'll probably see some of the old exam questions I had on transaction processing, but they're usually pretty. It's not that technical usually, because we haven't really gone through the technical. But I thought I would at least kind of give you guys some exposure to it. Okay, so with that, I think we can end lecture today, and the next lecture will be on security and authorization, plus a little bit on cloud computing. I'm not really sure if we're going to take up the full time next time, But once we do that, then we will have, and I might actually add in some other miscellaneous stuff that I think maybe needs to kind of just be mentioned. But after that, then we're going to have all the content for the exam for the course will then be closed off next Monday, and then we can kind of prepare for the exam at that point. Okay, if there are any questions, put them in the chat here. Yeah, for the lab 2 demonstration, take contact with the TAs. I think you need to book with them. Okay, any other questions? Okay, I don't see any other questions. So, okay, I'll catch you all later.